Welcome to the Geo Flo Design Calculators video series. This session will concentrate on a single geothermal heat pump application. Let's get started. First off, we need to go to the Geo-Flo website, www.geo-flo.com. You'll find a menu on the right-hand side. Design Calculators is where we need to go. So click on the Design Calculators link. Once you get to the Design Calculators, you'll find a place to log in with your email and password. It's a free account. Just click on Create Account if you don't already have one. Once you're logged in, you'll see your name at the top of the page. In this case, we're logged in as Mr. Geothermal. Now, the first thing we want to do is decide which calculator to go to. You can see here there's several panes of calculators. And since we're doing a single unit application, we need to first look at our pressure drop of the system, the ground loop piping, heat pump, and so forth. And then we can size a pump accordingly. So we'll just be looking at these two panes to start off with. So you want to click on the pressure drop calculators where the red circle is. Once we're on the pressure drop section, then we need to look at the calculator that works for our application. In this case, we're looking for a residential light commercial calculator, and we want the single unit with the outside header. We could also look at a single unit with an inside header, but in this case we'll choose the outside header for our example. Once you open the calculator, you'll find a color-coded drawing. In this case you can see blue piping, orange piping, green piping, gray piping, and those colors correspond to the appropriate section in the calculator inputs. Here you can see we have the dark gray piping, the blue, orange, and green as mentioned earlier. Alright, so the first thing we need to do then is select antifreeze. So from our drop-down list we can choose propylene glycol, ethanol, methanol, or water. And we also choose the percentage. We'll choose ethanol in this case. Alright, now we enter the percentage in. You can see here I've entered in 5%, and we do get an error message. Minimum level is 15%, and it also tells us what's typical. Let's try a larger amount. Now we put 40% in. Again, an error message. Maximum level is 30%. Typical, again, is 20%. So we'll stay with the 20%. Also notice that you'll have the freeze protection as well as specific gravity once the percentage is within that range. Once we have antifreeze, now we need catalog data for the heat pump. In this case, I've keyed in 12 gallons per minute at 10.2 feet of head. So we'll need to pull up that data from the heat pump manufacturer. And in this case, we're using a 4-ton heat pump. We'll look at the lowest entering water temperature expected. In this case, we're expecting 30 degrees. If it's warmer, we would look at a different temperature. If it's colder, we would look at a colder temperature. And then we'll look at the appropriate flow rate. Most heat pump manufacturers will have a nominal flow rate shown as the third flow rate, and a minimum flow rate for closed loop applications is the middle flow rate. Usually the lowest flow rate is for open loop or well water systems. So in this case we'll pick 30 degree entering water. That's the loop temperature coming back from the ground loop to the heat pump. 12 gallons a minute. This was a 4-ton system, so it's about 3 GPM per ton, which is fairly typical. And then we have 2 columns for pressure drop across the heat exchanger, foot of head, as well as PSI. PSI is typically used for servicing with a pressure gauge, but for pump design we'll use foot of head, and in this case we have 10.2 foot of head. Alright, so we're ready to start. We'll first start where the red asterisk is, and we'll look at heat pump piping first. That's this dark gray piping. In this case the example shows a hose kit. Alright, so this is our drop-down box. We've chosen 1-inch hose kit in this case. We could have also chosen polyethylene, several different types, PEX A, PVC, or even copper. And in the case of a hose kit, you'll notice it says the diameter of piping, ignore if using hose kit. So we don't have to worry about that. We do need the length of the hose kit, and this is one side only. So we use our standard hose kit of 6 feet on each side. And then also we can ignore this last input for elbows because it already includes the 2 elbows at the heat pump if we choose a hose kit. If we were using hard piping, we would enter the exact number of elbows in the system. All right, so now we're ready for the blue piping. You can see here the red asterisks again. We're looking at this blue piping from the flow center over to the building penetration. And again, we have a drop-down list. In this case, we're going to pick polyethylene 3408. We could have picked all these other choices as well. And now we need a size. For this 4-ton system, we'll use 1¼ high-density polyethylene. All right, then we key in the distance. Again, this is one side only. So we're going to key in 20 feet, which is from the flow center to the building penetration. And the number of elbows, again, one side only. In this case, we're using for our example 2 elbows per side, or 4 total. All right, now we can go on to the header piping. That's the orange piping that connects from the building penetration out to the ground loop header. And the header is where the multiple parallel circuits connect. So in the orange section, we again choose pipe type. I'll stay with polyethylene 3408. We again pick our diameter. Almost always the diameter would be the same for the header as it would be for the supply and return line, but it depends. It could also be larger. If we had an extra long run, we might need to lower the pressure drop. So it does allow us to change the different portions of the system. In this case, we have 100-foot one-way from the building penetration out to the header. Normally we don't have any elbows between the building penetration and the header, but we could, so there's space in here to add elbows. All right, the last section of piping is the green section. So you can see here where the red asterisk symbols are. This is the ground loop circuit. These are the parallel circuits that connect to the header. All right, so once again, we select piping. We'll continue with polyethylene 3408. We have to choose the size. In this case, we'll pick 3/4 inch, but we could use larger diameter depending upon the number of circuits, the loop configuration, and so forth. These are vertical loops, and we typically, with 3/4 inch pipe, we typically go with 1 bore per ton, or 1 circuit per ton. So that leads us to the next section, the number of ground loop circuits. If we stay with our 1 bore or 1 circuit per ton, that's 4 circuits. And I mentioned this is a vertical loop, so we'll have a U-bend at the bottom, and that's what we have here for the number of elbows. 2 elbows is that U-bend at the bottom. And finally, we need the length of that circuit. So this is actually the total length from where it connects to the supply header, down through the bore, through the U-bend, and back to the return header. And in this case, we had 175-foot bores, four 175-foot bores. So the total circuit is actually 350 feet. That's 150 feet, 175 feet down, 175 feet back. All right, so we've keyed all the information in, and it gives us a detailed report as we scroll down. So we know how much pressure drop is related to the heat pump, the hose kit, and so forth. Here's the number, though, that we're concerned with, the red oval, and that's the total system pressure drop for this particular layout. It's 31.6 foot of head at 12 gallons per minute. It also tells us how much antifreeze and total system volume we need, as well as flushing requirements. And we're assuming a parallel reducing header when we're talking about flushing requirements. There is a flush cart calculator as part of the same calculator package. So if the header is not configured as a parallel reducing header, you can always go back and find out flushing requirements if it's changed from what the assumption of this calculation shows. So then we have a system curve on the bottom, and if you follow the curve, you'll find that at 12 gallons per minute, it's about 31.6 foot of head. So this is just a graphic representation of the number above in red. All right, so now that we have the pressure drop calculation, you can see here the blue highlight. The next place we need to go is pump sizing. So we click on pump sizing, and we again go to a menu of choices. We can choose residential light commercial or larger commercial systems. In this case, we'll just look at a flow center like the picture shows here. This particular flow center is a variable speed flow center. So we'll click on pump sizing, flow centers up to 100 gallons per minute. And just like the pressure drop calculator, we have input at the top and results at the bottom. So we have now, from our pressure drop calculator, 12 gallons per minute at 31.6 foot of head. That's our starting point, and we're now ready to select a pump. In this case, I'm going to select the Magna Geo 32-140. That's a variable speed pump like the picture we saw earlier. Then we need to pick number of pumps. I'm going to try one pump on this application, see if I can get by with it. We also have our kilowatt hour cost if we want to look at operating cost comparisons. It's always a good idea to look at the operating cost of different pump scenarios so that we can give the customer the best value. We also have to choose the equipment type, and this has an effect on operating cost, especially with a two-stage or variable speed heat pump. They typically don't run on full load very often, so it does affect operating costs, especially for variable speed pumping systems. All right, so with our selection, we picked one variable speed heat pump. Let's take a look at the results. Our design was 12 gallons per minute at 31.6 foot of head. We picked one Magna Geo 32-140 variable speed flow center. And the actual system flow rate is 12 gallons per minute at 31.6 foot of head. So what that tells us is that it's dialed back the variable speed pump to match our requirements. In other words, it could have had higher flow rate if we let the pump run full out, which is where the system curve crosses the pump curve. If that's the case, it could have attained 13 gallons per minute, but we only needed 12. And in fact, if we did let it run full out, it would take 230 watts, which is not an advantage with a variable speed pump. We wanted to take advantage of all that runtime and part load. On a two-stage heat pump like our example, it runs about 80% of the time on part load. So let's take advantage of those lower flow rates, which equals lower energy consumption because this is an ECM motor on the pump. And in this case, with our 80% runtime and part load, you can see here that we have 78 watts on average. Now we could go back and change our assumptions. We do have an input for number of hours per year if your energy analysis software shows that it's something different from our assumption, which is listed on that input. But in the case of using our standard assumptions, you can see about 78 watts is our average power consumption, and our operating costs then are $39 per year if you take the average watts times the number of run hours. All right, so that's our selection, but we can also use different pump types. We looked at a variable speed pump first. Let's take a look at a constant speed pump. This is a UPS 2699. It's a 3-speed pump. We'll select high speed, so it's either on or off. The speed changes are set up at startup time. And we're going to go with just one pump. So let's scroll down and look at our output. Again, we have our same design conditions, but with one UPS 2699, we can only get about 10 gallons per minute. That is above the minimum required by the manufacturer's catalog, but it might be a little bit too close for comfort. So we'll need to go back and take a look at some other scenarios. And also notice that 172 watts, it's about twice the watts, even though it can't really attain what we're looking for. So let's go back, put in 2 pumps. All right, now we can certainly get the flow rate we need, but we're at 360 watts, and we're actually higher than nominal flow. We only needed 12 gallons per minute, and because this is just an on-off scenario, we're going to get 13.7 gallons per minute. Now the worst part is we get the same flow rate on part load as we do on full load, and we really don't need that much flow rate on part load. So in fact, we're running at about 4.5 times the energy usage as we were before with the variable speed pump. All right, so now we're going to go back to our pump selection, and we'll try those 2 pumps on medium speed. Let's see what happens. On medium speed, you can see now we have 12.4 gallons per minute, so we're just about right on nominal. That gives us the opportunity to adjust that flow if we do go with a constant speed flow center. And we do cut the watts by about 30 watts. We're still about 4 times as much operating cost as our variable speed, but we have helped a little bit. All right, let's go back and try another pump. A common pump for geothermal systems is a UP 26116. It has a little bit higher head, but it uses a lot more energy, so let's compare. We'll stay with 2 pumps since that's what we had on the 2699 selection. But take a look at our output. We now have 15 gallons per minute. We only needed 12. And these are not multi-speed pumps. This is a single speed pump. But also look at our watts. We're 7.5 times as much energy usage as our variable speed pump, 588 watts. All right, so that tells us we might be able to get by with only one of these 116 pumps. So let's change this to 1. And you can see our output. It's not as good as the variable speed pump. That variable speed pump is almost as good as two 2699s. But we can get 11.4 gallons per minute, so we're only off about half a gallon per minute from nominal. And we are at 269 watts versus 2 of the 2699s, which were 232 watts. So about 30 watts or so in savings here, about 60 watts savings versus the two 2699s. All right, so as you can tell, calculating pressure drop, pump sizing is a pretty easy endeavor with the Geo Flo Design Calculators. It also gives you the ability to do what-if scenarios like we did in this example. In this case, we're going to stay with our variable speed pump and our savings of energy. If you look at the total COP or EER for the system EER, system COP, when we have very few pump watts, we certainly affect the system EER and COP. So it's a big advantage from an operating cost standpoint. And in many cases, like this example, one variable speed pump can actually replace 2 constant speed pumps if we're comparing to the 2699. I hope this video series was helpful. If you have any additional questions or would like to do additional research, go to the website at www.geo-flo.com. Thank you very much.